Why I like math. This is Professor Derek Seitz. I am a professor of both mathematics and computer science. In this presentation, I provide personal and general information explaining why I like math. My traditional math education. Some information about the era of my math education. It was before electronic calculators. We used slide rules and numeric tables. It was before cell or smartphones. We used old-fashioned landlines. Before personal computers, only mammoth mainframe computers existed. Before Microsoft Windows and Microsoft Office. Some information about my formal math education. The different school levels or grades, all the way from elementary school, grades 1 through 6, junior high, 7 and 8, high school 9 through 12. This was up north. College, undergraduate 4 years, and graduate more than 2 years. In elementary school, subjects included counting, comparing, reading, writing, add, subtract, multiply, and divide. This is where I got my first glimpses of visual math in cow drawings that I made, first grade. I have a memory one day of writing with a pencil some numbers, and a teacher in one of my elementary classes walked by my desk and made the comment, "Did I write too small? I need to write bigger." I don't remember much else except that. I did use paper, pencil, and eraser back then. In junior high, see 2 question marks here, I don't remember much of what they talked about at all, except there was some more visual math, and I'll show what that was shortly in this presentation. High school was a traditional algebra, geometry, trigonometry, and pre-calculus. With algebra, was symbolic math, using variables, equations, formulas, and I upgraded from a regular pencil to a mechanical pencil. In geometry, it was classical Euclidean geometry with postulates, proofs, and theorems. It's a very interesting class. Trigonometry, right triangle trigonometry, not circular function trigonometry. And again, tables were used. There was no calculators. And interpolation, how you get finer answers from tables. Pre-calculus was limits, logarithms, more tables than interpolation. In my undergraduate college, studied functions, calculus, logic, number theory, statistics, linear algebra, differential equations, and other things that I don't remember right off. This built foundations, a broad view, and I upgraded from mechanical pencil to using pens and just crossing things out to erase rather than erasing with an eraser, which you can't do anyway when you have a pen. In my graduate school, I remember studying real analysis, complex analysis, group theory, graph theory, topology, and other things. And at that level, it involved deep dives and often felt like I was in outer space, wondering what this stuff was. First glimpses of visual math from first grade. We did drawings in there, and I don't remember much about first grade except for my cow drawings. I reproduced one here from memory, what I think it might have looked like. That's how I drew my cows. And of course we had probably crayons, maybe colored pencils, I don't remember. But here's some cows. And these simple cow drawings, whether I understood it or not, provided beginnings of the following math concepts: the concept of number, absolute and relative position, size and comparison, diversity and similarity, consistency and patterns, symmetry, and symbolism and visualization. This was very elementary, that's why it's called elementary school, but still the mind, through this visual work of drawing cows, all those skills begin to show up on the scene. To get into the visual math in 8th grade, there's a sequence here. First, triangle area. Here is a green triangle, right here. It has a height h and a base b. The three corners or vertices, A, B, and C, those points. And the height is a perpendicular dropped from that vertex to the opposite side. If you take this triangle and flip it and reproduce it over here, like so, you end up with both of them together being a parallelogram. And then, if you cut out this little piece right here on the left and move it over here, you get a rectangle right here. The area of triangle ABC, of this green triangle, is 1/2 the area of the parallelogram, which has twice that area, two of those triangles, 1/2 that. But that's equal to 1/2, just carrying that down, the area of the rectangle. By moving this piece over here, we get a rectangle. And what is the area of the rectangle? The two dimensions are the base here is what this segment right here is, because we move this piece over here, and so altogether you now still have B down here, and H, 1/2 base times height. This is a simple visual proof that the area of a triangle is 1/2 base times height. Moving on to circles. There's a circle here labeled C1. It has a center at point M and a radius of R. All the points that are equal distance from the center, a distance of R from the center, make up the circle. D goes all the way across. It's the diameter of the circle with two endpoints, E1 and E2, which are on the circle. The length of D is twice the radius. And the circumference is a distance all the way around the outside of the circle, what we normally think of as perimeter of a shape. So I indicate that with a little c. Pi, the Greek symbol pi, is equal to the ratio of the circumference divided by the diameter. And it's always the same regardless of what circle you're looking at. All circles are similar to each other, and so this proportion is a universal constant for all circles. And it is a constant, it's the same value. It happens to be an irrational number, that's not a ratio of two integers, and it can be approximated by 3.14, although in reality, being irrational, it goes on forever with decimal places that never repeat in any pattern. Hard to imagine those irrational numbers. If we rearrange this equation, pi equals c over d, we get c equals pi times d, pi times diameter. Just multiply both sides by the diameter to clear the fraction. And since the diameter is 2 times the radius, this gives us an alternate formula for the circumference, 2 pi r. Circumference is pi times diameter, which is the same as 2 pi r. Moving to circle area, this is what I was shown in 8th grade that impressed me visually, got my attention. I still remember it to this day. Again, we have a similar diagram as before. C1, same circle. C is the circumference, which is 2 pi r. We're going to look at the area of the circle, and we'll start by looking at the area of triangle AMC. AM is the center, and C. It's a triangle here shown in this diagram with 2 points on the circumference, and the height of the triangle goes down here. It's not equal to a radius. It comes a little bit short. But that's the triangle we're going to look at, AMC. If we were to repeat that same triangle and put it next to it, 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 as it says here, make many such triangles adjoined to each other so that they almost completely cover the area of the circle. They all have their 1 point at M, and they have 2 points on the circle, and you make a bunch of them all the way around. And the sum of the areas of those triangles will approximate the area of the circle. You can see that visually. And as you make these triangles smaller and smaller, by that is meant the 2 points A and C, if they get closer and closer together, such that H gets more and more closer to R. So as you make them a little narrower, would be the better word rather than smaller, narrower triangles, then H will approach R. Get closer and closer to R. And the sum of all the bases of these triangles across here will approach the sum of them. The sum of all those bases will approach the circumference of the circle. Because there'll be all little circles with these little bases all the way around. So the sum of their areas approaches the area of the circle, and the sum of their bases approaches the circumference of the circle. So the area of the circle is the limit as the bases approach 0 of the sum of the areas of the triangles. That's what this notation means here, the sum of the triangle areas. That's the limit of the sum of 1/2 base times height. That's the formula for the area of each one. It's the sum of all those. You can bring the 1/2 out front, and then we have base times height. Remember that circumference is what? It's 2 pi r. So if we have here the base is approaching 0, it's not going to be equal to 0, but the sum of the bases are going to approach the circumference, and H will approach R. So H here, as we take the limit, we replace by R, and we bring the 1/2 out front, we bring the R out front, and what are we left with? If we bring the 1/2 out front and the H, which is R in the limit, we're left with the sum of the B's. And so we have the 1/2, the R, and the sum of the B's is left in there in this sum, but the sum of the B's is the circumference. So if you follow there, just looking at what a sum is, and if there's a common factor, you can bring it out front, bring the 1/2 out front, you bring the h out, but in the limit, h approaches r, so it becomes r, and you're left with the sum of the b's still in parentheses, and they're equal to the circumference in the limit. But the circumference here is 2 pi r, so we replace circumference by 2 pi r. 1/2 times 2 cancels out. R times r is r squared. We're left with pi r squared. So this is a visual proof of the area of a circle based on areas of triangles. My first test that I can remember was near the end of 8th grade. After being introduced to visual math, as I just explained, I was in class and someone came in and they gave us one page containing 2 columns of calculations involving integers and simple order of operations, I think. I don't even really remember much about it, except for it had 2 columns and there were calculations. Maybe around 20 problems in each column. And we were given two minutes. They didn't tell us that. I started working on it, and after 2 minutes, time's up. I was surprised, shocked, and disappointed. I had only completed a few problems. I don't know, maybe 5 at most. We later found out that this test was used to determine who would be in the advanced math class next year in 9th grade in high school. Well, I'm a slow thinker. If there is a timer, I get stressed out. Not by the timer, but by the fact that I only have limited time to do something. Needless to say, I was not in the advanced math class at the start of 9th grade. However, I was uncomfortable in a regular math class. The other students did not know many basic things, like how to add fractions. I was bored and not happy. I appealed to the school counselor, and I was moved to the advanced class on a trial basis. All 4 years of high school, I retained my spot and moved along in that advanced class. Some things to understand about math. Math is the language of science, including biology, chemistry, computer science, economics, physics, to name a few. It's the foundation of visual art with proportion, perspective, and symmetry. It's the foundation of music with differences, combinations, sequences, and patterns. It's the foundation of reasoning, including analysis, deduction, evaluation, induction, inference, and logic. I have a quote here that fits very well with that last point from the King James Bible, Isaiah 1:18, first part. "Come now and let us reason together, saith the Lord." Reasoning, an important part of, important foundation of math. Math is also symbolic and visual and numerical as well. And visual involves external views of what you see with your eyes and also internal visualizations in your mind. It's wide and deep. Math is infinite and infinitesimal. It has an integration of order and randomness. Math gives us a historical legacy of the discoveries of its past explorers. It's for all people of every culture and age. a limitless adventure with endless worlds to explore, an ocean for personal creativity, a mirror that shows us the limitations of human reasoning. There's a famous pair of theorems that you learn when you get into more advanced mathematics. Gödel's incompleteness theorems prove that there are truths that are impossible to prove. Here's a quote that ties right into that. Deuteronomy 29:29, the secret things belong unto the Lord our God, but those things which are revealed belong unto us and to our children forever. Human reasoning has limits. Math is correct. You get the answer. If you did everything right, it's correct. It doesn't lie. It's consistent. You get the same answer if you do it right, different ways, still the same answer. It's precise. It's theoretical and practical. Part of a spectrum there. Some things are in outer space. You wonder how they're ever going to be applied, and other things have many, many applications in different disciplines. Math is universal. It's a language that transcends spoken human languages. It's timeless. How math helped my business career? I worked for 33 years in the professional software development industry. And here are some of the roles, some of the jobs that I had during that time. A computer maintenance programmer, new development programmer, software designer, software architect, software development team manager, software development process engineer, user interface designer, and systems business architect. I could talk at length about all those different things, but the point here is that I have a lot of experience in the business world, especially with computing. Some math skills that help me in these roles include the following: the ability to analyze and solve problems. That is one of the foundations that you learn in mathematics. Logical reasoning skills help me. I had an advantage over people without a math background, without strength in mathematics. Also, I had good written and spoken communication skills, which I developed through mathematics. Pattern recognition and organization skills were very helpful. And the ability to represent concepts symbolically, this computing world, visually, different kinds of output, user interfaces, and numerically, databases and data relationships. Also, in my business work, I worked in different what's called business domains. It's not just about knowing how to deal with computers. You have to also solve problems in the real world. Here are some of the business domains that I worked in. Check image processing systems for United States commercial banks, United States Federal Reserve banks, and international banks. Branch banking systems, central bank account processing systems, accounting systems, insurance systems, financial investment systems, public sector, which means in this case a state government, driver's license systems, and public sector criminal justice systems. All those different domains. Each business domain has its own unique vocabulary, its own unique business rules that are even unique by customer, oftentimes, or state, and its own unique business processes. Some math skills that helped me get a grip on the business domains included definition rigor skills. In mathematics, everything has definitions, and it's very rigorous, and that helped with the vocabularies and business rules in the business domains. Theorem proving skills helped with how different business rules actually are derived from other business rules and impact. There's like theorems that they have ripple effects. Set categorization and organization skills, being able to organize things and understand how things are organized in businesses. Relationship function and formula skills. Many of these domains have formulas that they use, mathematical functions that are used, processes, and also composition and transformation skills, which come into play with business processes where data is transformed along a sort of a business pipeline that it goes through. Also, go shift gears here, art. I have some digital art. The following two digital artworks are from a program I wrote using different starting parameters for each work. My program uses a 3-layer architecture with a model, view, and controller. The model is the data focus. The view is the output, the user interface, and then the controller is the algorithmic processing that ties everything together. This is a standard architecture used in computing. My first example is a deterministic example. I call the following work Royal Ships. Its starting parameters, which incorporated the Fibonacci sequence for mathematics, had no element of randomness. That means it's deterministic. It's going to produce this same thing. There's no randomness about it. And you see here, Royal Ships. There's 7 of them. 1, 2, 3, 4, 5, 6, 7. A non-deterministic example, I call this merchant ships. In addition to its deterministic algorithm, its starting parameters incorporated randomness, ability to get random numbers as part of the starting locations in this algorithm. And you see here these ships in the water that were produced and now serve as a form of art, digital art, mathematics. My goals as a math educator. I have taught college-level math courses for 15 years, including both traditional classroom courses and web-based online courses. The following are my main goals as a math educator. To promote learning skills. That means that the students learn how to learn, including time management. To promote analytical skills, including being able to reason from cause to effect. To promote technical writing skills, including clarity. And to promote appreciation of math. One of the reasons I made this presentation in this video. In conclusion, another Bible verse, very appropriate here, from James 1:17. Every good gift and every perfect gift is from above, and cometh down from the Father of lights, with whom is no variableness, neither shadow of turning. I am thankful for the universal gift of mathematics. I hope you benefit from your study of mathematics.